All right, in the last video, I gave you a physical interpretation of what the divergence of F at a point represented, and that was flux density. Now, in that, I gave you that we had a point surrounded by a sphere. So we would have had P naught surrounded by a sphere of radius A, and I chose to use a sphere there and then say I could take the limit as the radius of the sphere shrunk to 0 of the flux across the surface of the sphere, oriented out, divided by the volume of the sphere. Okay. Did that because it's simple to describe a sphere, because there's just one number that's going to describe the size of the sphere, and that's the radius. Okay. I'm going to switch that over, however, because there's nothing that says that the region that I'm going to shrink to a point has to be a sphere. So, for the informal argument that again is presented in div, grad, curl, and all that by H.M. Schey, that's the informal argument that I'm going to be presenting here, they found that it's actually easier to work with a rectangular box. And we're going to take that rectangular box and we're going to shrink it to a point. And again, the divergence of F is just the limit of the flux over that boundary divided by the enclosed volume. Doesn't matter whether it's a sphere that you're shrinking to a point or a box that you're shrinking to a point, as long as you've got some region that encloses that point, its boundary surface, and you're calculating the limit of the flux across the boundary surface divided by the enclosed volume. So they're going to present us with this. We're going to have a point P naught, which is going to be the center of our rectangular box. The sides are going to be delta x, delta y, and delta z. That means that the volume of this box I can write as delta v, which is just the product, delta x, delta y, delta z. Okay, excellent. Then I've got to have my vector field, f. I've just named the component functions little f, little g, and little h. Those are the real valued component functions. We're going to have this box that's centered at the point P naught. Its boundary surface S is piecewise smooth. When I have a rectangular box, there are 6 parts to the boundary surface. So I've just sort of labeled them. The boundary surface on the front, that would be this front rectangle here. The boundary surface on the back. The boundary surface on the top, on the bottom, on the left, and on the right. And that's going to be our boundary oriented out. So, according to the definition, the physical interpretation of divergence, it's the limit as we shrink all 3 dimensions of that box to 0. So as delta x, delta y, delta z all go to 0, which I can represent by this ordered triple, just going to 0, 0, 0. Okay. Of the flux across that boundary. Now, because the boundary is piecewise smooth, this would just be a sum of the flux across all 6 of these boundary surfaces, divided by the volume. But according to the plug and chug definition of divergence, that should actually be just the partial of f with respect to x at P naught, plus the partial of f with respect to y at P naught, plus the partial of h with respect to z at P naught. That's just del dot f evaluated at the point P naught. And looking at it, it does not seem remotely obvious that these 2 things should be equal. What I'm going to do is I'm going to work through what we get from this limit to show that we actually get that. I'm actually going to do just part of that argument because, of course, this involves 6 different integrals. What I'm going to do is just work with the first 2. They sort of come in pairs. I've got the front surface and the back surface. Okay. I'm going to have the left surface and the right surface, the top surface and the bottom surface. So I've got 6 surfaces, but that's 3 pairs of surfaces. Each one of those is going to contribute one of these terms to the plug and chug definition of what the divergence of f at P naught is. So I'm going to just evaluate this over the front and back surfaces, show that that's going to lead to this term, and then by an extension, if you were to do the top and bottom would actually give you this term, the left and the right would actually give you this term. And I'll leave it as an exercise if you want to work through it, to work through those. But I think just working through that one pair and seeing that it gives us this term is sufficient for us to see the connection and see why this works out. Okay, so if I want to work over the front surface, so let's just say I'm doing the double integral along S sub f. I'm just going to abbreviate for the front surface, I'm going to abbreviate it with an f. So if I'm working along this with f dotted with n ds. Now, what's nice about choosing a rectangular box rather than choosing a sphere is that all of these surfaces are just portions of plane. They have a constant normal vector. And if I'm on the front surface and I'm supposed to be pointing out away from the center, that means that my normal vector is pointing straight out. So my normal vector on the front is just 1, 0, 0, which is kind of nice. Okay. Now, for f, here's where I'm going to actually do an approximation, because we're actually evaluating f at any point along this front surface. But I'm going to just take a look at this very frontmost point. So if I look just at this front surface, okay, its dimensions are delta y and delta z. Its front point is directly in front of P naught. And let's say that P naught, let's give it coordinates, x naught, y naught, z naught. Okay. So if I've come straight forward from that point, I haven't changed the y and z values at all, but I have increased the x value. If this length was delta x, I've covered half of that, because P naught would be right in the middle, so I've come half of delta x forward. And then the points on the back would be x naught minus delta x over 2. So this point right here is x naught plus delta x over 2, comma, y naught, z naught. That's the exact center of this front surface. Now, we're supposing that we're going to be ultimately shrinking this thing to a point. So this is going to be a very small surface eventually. So I'm just going to approximate. Now this right here is what makes this an informal explanation, because I'm going to replace this with something that's close to it but not exactly equal. So this is not a fully rigorous proof to show that this is exactly right, but this is just an informal suggestion of why this works. Okay. So I'm going to say this is close to, if I were to integrate over that front surface, f evaluated at x naught plus delta x over 2, y naught, z naught. Let's clear some space. Dotted with 1, 0, 0. Now that's not an approximation. That is exactly what is normal to this surface. So this is where I'm making an approximation. This is usually what we do when we create a Riemann sum. Essentially, it's almost like I'm saying, you know, this is going to be such a small surface. Let's create a Riemann sum with just one rectangle. Okay? So I'm using that as a representative point. Okay? But notice what that's going to give me then. Okay? Because this is just f evaluated at x naught plus delta x over 2, y naught, z naught. And then g, that would be my second component function, evaluated at that same point, x naught plus delta x over 2, y naught, z naught. H, evaluated at x naught plus delta x over 2, y naught, z naught. Dotted with, whoops, let's close off that vector, dotted with 1, 0, 0. And then we're still integrating ds. But because I'm dotting with 1, 0, 0, these two components are going to just entirely drop out of the problem. So what we're going to get is just the double integral along that front surface of f of x naught plus delta x over 2 y naught z naught ds. Because I get 1 times this first component, 0 of these, and 0 of these. So this is what I get when I evaluate that dot product. But that's constant. So what I'm going to get is just that constant times the area of that front surface. So that's going to be f of x naught plus delta x over 2, y naught z naught, times the area of that front surface is just delta y, delta z. Because remember, that front surface looked just like this with a delta y and a delta z. That's this front surface that I've got right here. So this approximates the flux across that front surface. What I'm going to do next is approximate the flux across the back surface, and then, since we're looking at flux density, take the limit of that divided by the enclosed volume. Of course, overall, I would have 6 integrals, because I would have front and back, plus left and right, plus top and bottom, and then all divided by the volume. But that's just 6 pieces. I'm just going to be looking at the first 2. Okay. So I'm going to stop this video here. We'll pick up with the back surface in the next one.